Good afternoon and good evening, everyone. So today is the week 8th of the tutorial session of the course Principles of Signals and System. So basically in this week we will mostly discuss about some of the problems based on the whatever we have studied till now, mostly based on Fourier transform and also some on Fourier series. So we'll start with some of the questions based on this. And we have already done lots of questions, which is discussed in the week 8. We have done it before only. So today we'll do some of the new questions. Wait for 1 minute. So we'll start with the first question that is based on inverse Fourier transform and also based on the Parseval's theorem. So the question is consider xt is given, that is e raised to the power of minus t when t is greater than 0. And x omega is the Fourier transform of xt. Then we have to find this integral 1 by 2 pi integration of x omega with respect to d omega from the interval minus infinite to infinite. So in this question, what we have to do, like this, you can see that this formula is similar to inverse Fourier transform if you add here e to the power of minus j omega t and substitute t tends to 0. Okay, so we'll do the same thing. So here we will write like xt is equal to 1 by 2 pi minus infinite to infinite x of omega e to the power of minus j omega t d omega. So this we can write this using the inverse Fourier transform formula. So in this equation, if we put t is equal to 0, then it will be similar to the given integral whatever is asked in the question. So put t is equal to 0 in equation 1. Let's suppose this is equation 2, then equation 1 will become equation 2. So when you put t is equal to 0, in the left hand side it will be x of 0, that is equal to 1 by 2 pi integration of minus infinite to infinite x of omega e of 0 d omega. So now this will be 1 by 2 pi integration from minus infinite to infinite x of omega d omega. So here we will get the integration of 1 by 2 pi. This integration is equal to x of 0. So we have to find x of 0. Now we know that our xt is equal to e to the power of minus t when t is. So we are discussing about the questions, some of the questions based on Fourier transform. So I will just explain from the starting so that someone has joined now. So like in this given question, xt is given, the signal xt, that is e raised to the power of minus t, that is t is greater than 0. And it is 0 when t is less than 0. So x omega is the Fourier transform of xt, and we have to find this integral. This integral we have to find. So this integration is similar to the inverse Fourier transform formula. Only thing is missing is here e to the power of minus j omega t. So in that way we have written the same thing, and we have put here t is equal to 0. Then this equation 1 will become like equation 2, and here we will get x of 0, that is equal to 1 by 2 pi integration of x omega d omega, what is asked in this question. So we have to basically find x of 0. So x of t is given, that is e raised to the power of minus t when t is greater than 0, and 0 when t is less than 0. So at t is equal to 0, it is not defined. So we will use Gibbs phenomenon, that is used to evaluate the value of function at discontinuities. So it basically just average the value at whatever is the discontinuous point. Just take the left side and right side, the value in the left side and right side, it's average the value. That is known as Gibbs phenomenon. So here x0 is equal to x of 0 plus x of 0 minus divided by 2. So when you put x of 0 plus, it will be e to the power of 0, that is 1, plus x of 0 minus is 0 here, divided by 2. So that is equal to half. So for this question, the answer will be half. So this was a very simple question based on the inverse Fourier transform formula. So now we will see one important result, that is one shortcut. Like whenever we have to find, like this is the property of duality what we have studied. So if the Fourier transform of like del t is 1, Fourier transform del t is 1, we know. Then the Fourier transform of 1 will be like 2 pi, and here just you substitute omega, okay? 2 pi of del omega. So in this way, like let's take one more example. Uh, let's suppose the Fourier transform of e to the power of j omega t naught is given as 2 pi del of omega minus omega naught. Okay. Then we have to find the Fourier transform of del of t minus t naught. So whatever is here in the omega term, if we are substituting as t, then the Fourier transform of this will become 2 pi, like 2 pi into del of like this term into omega. So what happens, what we have to do? So here, like here it is 2 pi is multiplied here. So we have to divide it by 2 pi, because uh, for 2 pi del t minus t naught, it will be like of 2 pi e of j omega naught t. Okay, omega t naught. So in this term here, what we will do, this 2 pi will get cancelled. So we will get the Fourier transform of del t minus t naught is e of j omega t naught. So we'll take one more example like this, then you will understand. Like let's check. of signum t. Fourier transform of signum t, we all know that that is 2 by j omega. We have already proved this in the last lecture. So now if we have to find like of Fourier transform of 1 by pi t, then what it will be? For 2 by jt, it will be 2 pi of signum of omega. Okay. Now, for making it 1 by pi t, what we have to do? We have to multiply 2 by jt into pi. In the in numerator, we have to multiply by j, and here in denominator, we have to multiply by 2. Then 2 will get cancelled and it will become 1 by pi t. So we have basically multiplied by j by 2 pi. Okay, multiplied by j by 2 pi. So in that side also we'll multiply. So it will become j by 2 pi. If you will multiply, in this 2 pi will get cancelled and the value will be j of signum omega. Okay. So we have to multiply it by, here we have to find like 1 by pi t. So it will be first 2 pi of signum omega for 2 by jt. Okay. And when you multiply by j by 2 pi, then this 2 will get cancelled. It will be 1 by pi t, and we will get that will be j of signum omega here. So this we can use it. This property we can use it for finding the like Fourier transform very easily. Sometimes some complex Fourier transform. This is just a shortcut, just a practice example based on the shortcut. So now we will see some one more example. Before that, we will see like Fourier transform of periodic signal. So let's suppose a signal xt is given, a periodic signal xt is given. After that, we'll solve a question on that also. And the Fourier series of xt is represented as xt is equal to summation of n is equal to minus infinite to infinite. This Fourier series coefficient Cn e to the power of j n omega naught t. So in this way we can represent xt. So now if we take the Fourier transform on both the sides, so on the left hand side we will get x omega. Fourier transform of xt is x omega, and right side we have to take the Fourier transform of this term. N is equal to minus infinite to infinite. The summation of Cn e to the power of j n omega naught t. So in this, so this will become n is equal to minus infinite to infinite. Now Cn will come outside, and we have already done here that Fourier transform of e to the power of Jn, like j omega t naught is 2 pi del omega minus omega naught. So here Fourier transform of e to the power Jn omega naught will be 2 pi del omega minus n omega naught. So we can write 2 pi outside of summation as is a constant term. So in this way we can find. So let's take an example, like we'll take some periodic signal. The basic one is like impulse train. We'll take that and we'll find the Fourier transform of that. So first we'll draw impulse train. So Fourier transform of, find the Fourier transform of given impulse train. So at the interval of Ts, there is a impulse like this. So this is the impulse train. We have to find the Fourier transform of this. So first of all, how we can represent this impulse train? It is a periodic impulse trains with a fundamental period of Ts. You can see that after every Ts unit, it is repeating. So the fundamental period is Ts. So we can represent this as xt is equal to summation of n is equal to minus infinite to infinite del of t minus n of Ts. Okay. And the omega naught for this will be 2 by 2 pi by Ts. So now what we will do, we will first consider xt over a one period, that is like between minus Ts by 2 to plus Ts by 2. So the period is like Ts, so we can take any of the, this is one period we will take minus Ts by 2 to plus Ts by 2. And so in this we will see first, so we'll take xt in between minus Ts by 2 to Ts by 2. So here the impulse is located at t is equal to 0. Okay. So xt is equal to del t when t is from minus Ts by 2 to plus Ts by 2. Okay. Then we know the formula of Fourier series coefficient, that is Cn is equal to 1 by Ts minus Ts by 2 to plus Ts by 2 xt e to the power of minus j omega naught nt dt. So in this way we can find. So what we are going to do, like we have to represent in this form x omega is equal to 2 pi cn of del omega minus n omega naught. So for this we have to find this Fourier series coefficient cn. That's why we have used the formula of Fourier series coefficient. And now here we will find. So after this, when we will substitute cn, we will get as 1 by ts. It will be del t because the impulse is located at t is equal to 0, e to the power of minus j and omega naught t dt. So impulse is located at t is equal to 0. So this integration will converge to 1. So it will become 1 by ts into 1. So the value of Cn is equal to 1 by Ts. Now in the previous section, what we have seen from the like definition of the Fourier transform of periodic signal, we have seen that x of omega for a periodic signal is 2 pi summation of n is equal to minus infinite to infinite Cn del of omega minus n omega naught. So here it will be omega minus n of omega naught. Here we have seen in the previous section this part. So we have used this, and here we will get x omega is equal to 2 pi Cn is our 1 by Ts, 1 by Ts summation of n is equal to minus infinite to infinite del of omega minus n of omega. And also we know that 2 pi by Ts is omega naught. So we can write this as omega naught summation of del of omega minus n. So this is one of the question. Now we'll solve few more questions. And we can also draw this impulse train also in the frequency domain. Like you can see here. In frequency domain, this axis will be omega and the y-axis will be x of omega. So in this, what is the value? That is omega naught into del of omega minus n omega naught. So here it will be omega naught. In time domain it was 1, but here it will be omega naught. And what will be the duration? Duration will be like it is n time of omega naught. So it will repeat after omega naught. So, so we'll take some other example of Fourier transform.
Uh, sir,
Uh,
just one thing, sir. In that frequency domain diagram of impulse train,
yes,
the
sir.
height is omega naught,
Yes, yes.
height, and
Yeah, we can
the
see that.
axis is omega naught, the height is omega naught.
Yeah, height is omega naught because here you can see the amplitude is multiplied with omega naught with the impulse train, and this is repeating after n omega naught. So when you substitute n is equal to 1, so it will go to omega naught, then n is equal to 2 omega naught like that.
Okay, so this is also called the Coombe filter, right? For sampling.
Which
Coombe filter is another name for this.
I don't have idea of Coombe filter.
Sampling filter.
Yeah, yeah, sampling filter. Yeah, that is used in
Okay,
sampling
sir.
technique also. I don't know the name of Coombe filter, but sampling technique we use this. Like sampling of any signal, we use this filter.
Thank you, sir.
Mm. So a point to be noted here. So this is also known as Coombe filter, and this is like used in sampling also. So we will study in the next lecture, I guess, next week, the sampling technique. And now we'll take another example. Like based on whatever properties we have studied, we will solve using those shortcuts the Fourier transform. Like a signal xt is there. Like if xt has the Fourier transform of x omega, then find the Fourier transform of given signals. So let's suppose the first one is like x1t, that is equal to x of 1 minus t plus x of minus 1 minus t. So if we have to find the frequency transform of this, we know that the frequency transform of x1t is x1 omega. So here we can write x1t. So in this question, when you do the frequency transform on both the sides, in left hand side it will become x1 omega. In right hand side, here you can see the time is in minus t. So we have also studied about the like time reversal properties. So in time reversal properties, what happened? X of minus t have the frequency transform of x of minus omega. So here it is like x of minus of t minus 1. Like 1 minus t can be written as minus of t minus 1. So in this case, it will become e to the power of j omega x of minus omega. Okay. And the second part, this is minus of 1 plus t. So minus of 1 plus t it is there. So it will become e to the power of minus j omega x of minus omega. So now we'll take x of minus omega common. So it will become like this. So now this is simple. We can like break it into cos term because cos omega plus j sin omega. So here this sine term will got cancelled here. So it will become 2 of cos omega into x1 of minus omega. So this is the Fourier transform for this one. So we'll take another example also. Uh, like let's suppose the Fourier transform of xt is given as x omega. Then find the Fourier transform of xt is equal to x1t is equal to x of 3t minus 6. So here x1t is defined with respect to xt only, that is x of 3t minus 6. So here like time scaling has been done. So we will use that. We know that for time scaling, like the Fourier transform of xat, it becomes 1 by mod of a x of omega by a. So this is the Fourier transform of xat when time is scaled. So here also it is scaled by 3 units. So we can write it as x of 3 t minus 2. So now when you do the Fourier transform on both the sides, what we will get? X1 of omega, that will become, here it is scaled by 3 units. So it will become 1 by 3 x of omega by 3 and e to the power of minus 2j omega. So in this way we can simplify, and we can take some more examples. Let's suppose another signal is there. Find Fourier transform of, like those properties are very useful to this won't be asked directly in the exam, but this if you know these properties and all, we can simplify the very long and complex question easily. So x3, yes.
See, 3t minus 6. Why can't we consider 3t first using the formula minus 6 as a time shift method?
Yeah, that also we can do. In both the way, we'll get the same answer.
No. Is it so?
Like, but we have to first, when you do, when we are scaling here, no, so we have to take three common here.
No, okay. No, whatever
See,
you understood. So my logic is, without taking common, first, okay, so Fourier transform of x of 3t.
okay, if
Then,
you take x of 3t, then it will become 1 by 3 of x of omega by 3. But we have to do this also, no? Like,
it's different, right?
it will be different. Like, it won't be same because uh, for like if you take here, like if you want here t term, then we have to take three commons. It will become t minus 2. This t minus 2 is amplified by 3.
Yeah.
So if you take like first 3t, then how you will add here minus 6? You cannot add. No, you have to add only, like if you take 3 common here, you cannot like we have to write this term single only. You cannot break like this, no? X of 3t minus 6 is equal to x of 3t and then minus of x of 6. These things are rubbish. No, this we cannot do. We have to take together only this term, 3t minus 6.
Okay. Okay, sir. So, sir.
If we can if sometimes if we can like separate, there will be multiple units of time and all. In that case we can do, but at the last this term will come. This should come only. 3t minus 6 should come. Our main objective is to transform 3t minus 6 in the simpler form, like in the form of t. So we'll take one more example, like x2t is given as, let's suppose, uh, find the Fourier transform of x2t, that is given as del of x squared by del of t squared t minus 3. Means double differentiation. Here it is there. So in this term, we know that when the differentiation of xt dt is there, and we have to find the Fourier transform of this, then this becomes j omega into x omega. This d by dt, we can replace it by j omega. So here it is twice differentiation. So we have to replace it by j omega squared. So the x2 omega, if you take the Fourier transform on both the sides, it will become j of omega squared e of minus 3 j omega x of omega. So this will become now my j squared will be 1 omega square into e of minus 3 j omega x omega. So whatever properties we have studied in the last lecture is very useful. We can take one more example. So this time let's suppose x3t, that is equal to this third example of this point, t into d of xt by dt. So this is given. So we have to find the Fourier transform of this x3t. So let's suppose this term we consider as phi t. Then phi t is equal to, let's suppose, d of xt dt. Then we have just now did the Fourier transform of this dxt by dt is j omega s omega. So phi omega is equal to j omega of x into x omega. So now here x3t, that is equal to t into phi t. So, and we know that whenever when it is multiplied with like t, uh, here we have already studied in one of the property, like the Fourier transform of t into xt, that can be given as j of d of x omega d omega. So we will use that property. So here x3t is equal to t into phi t. So when we have to do the Fourier transform of t into phi t, this will be j into d of d omega, and here differentiation of phi omega. And phi omega is j omega x omega. So differentiation of j omega x omega divided by d omega. So now this will become like this j is constant, so this j will also come out, j square. Now here it will be simple, like x of omega d omega by d omega is 1 plus uh, omega into d of x omega by d omega. So this will become j square will be minus 1 square, that is 1. So it will minus 1, it will become minus 1, and here it will become j is root under minus 1, so the square will become minus 1. I think in previous example I have told it become sorry 1. Sorry for that, because it is root under minus 1, so it will become minus 1. So here it will be minus of omega into d of x omega by d omega plus x of omega. So this is the final answer for this question. Like x3 omega is written in terms of x omega in this way. So all these properties are very useful for solving the question. So we can solve using the properties whatever we have studied. Now we can see some other questions also. Just wait for a minute. क्लास चल रहा है. So now we will take a question. There is a rectangular pulse is given xt, that is from minus 1 to 1, so this is a xt is a positive rectangular pulse from t is equal to minus 1 to t is equal to plus 1 with unit height as shown in the given figure. Now we have to find the value of find integration of minus infinite to infinite x of omega mod of x omega square d omega. Here x omega is the Fourier transform of xt. So this is given. We have to find the this integration. So in this question, like we can write, first we will, what we have to find is minus integration of mod of x omega square d omega from minus infinite to infinite. This we can write it as x of omega into x conjugate of omega. So this will become mod of x omega square. So now this x omega term we can write as from the formula frequency Fourier transform. So x omega is integration of minus infinite to infinite xt of xt into e to the power of minus j omega t. So we'll write that. So this term is from the x omega, okay, and this is multiplied with x conjugate of omega and then the integration with respect to d omega. So in this we can write now integration of minus infinite to infinite. So we'll take x conjugate of omega into e to the power of minus j omega t d omega first and then xt dt later on. So now this term will become like when you do first we will multiply it with 1 by 2 pi and divide also by 1 by 2, sorry, multiply with 2 pi and divide by 1 by 2 pi. So we will get the inverse Fourier transform here. So here divide by 2 pi x of omega into e to the power minus of j omega t conjugate of d omega and then xt dt. So after all this, we will get here 2 pi and this will be like x conjugate of t here and multiplied with xt dt. So this will be the mod of xt square. So why we have done that? So that like our signal is given in the form of xt. So now we can simply do this integration. Mod of xt squared will be also 1 and the range is from minus 1 to 1. So this integration will be from like 2 pi mod of xt squared. So this will be minus 1 to 1 into dt. So now it will become 2 pi into 1 minus 1 will be 2. So it will be 4 pi. So the final answer will be like the question was also minus infinite to infinite x of omega mod of x omega square d omega that is equal to 4 pi. This is a simple way to solve this question. Like first we have transformed into xt and then we have solved it. So we can take some other concepts. We'll see what is like correlation, auto correlation and cross correlation. So like auto correlation is between like relation between the one signal only, one type signal only, like it is relation with xt itself. And cross correlation there will be two signals, so like xt and yt. So first we will see auto correlation function. This is mainly taught in communication system. So here we will see the simple basics of it. So like autocorrelation functions, it gives the correlation of functions with its shifted version. Like let's suppose xt is a signal, so it autocorrelation will be given as integration of xt into xt minus tau dt. So it is just the relation with its shifted version. So xt and now xt is shifted by tau unit, that is t minus tau dt. And we can write this as in this way also, like x of t plus tau into xt. In both the term, here you can see that xt is shifted by tau unit. So here xt is power signal, so it auto correlation is given as rx tau t tends to infinite. We will take for one period for power signal, that is minus t by 2 to plus t by 2 x of t into x of t minus tau dt. This we will do if xt is power signal. We will take for one period. If xt is energy signal, then we'll do for the continuous time axis. Like there are for like properties also. So we will not go into the proof of those properties, but we will see what are the properties of autocorrelation function. Like this is very useful in solving the questions of GATE. In recent years, lots of questions are asked on this autocorrelation function, and these properties are very useful. So like the first one is this autocorrelation function is an even function. This means Rx of minus tau will be equal to Rx of tau. Okay, so autocorrelation function is even function. We can prove this also, but right now I think not required that much. In communication system, all these proofs are taught. And also autocorrelation function has its maximum value at origin. So Rx of 0, mod of Rx of 0, that will be maximum. So it will be greater than Rx of tau or any value of tau. It may be equal when tau is equal to 0. The third property, like whenever we do the convolution of signal with its time reversal, then it gives the autocorrelation function. Like Rx of tau, that is equal to x of tau convolution with x of minus tau. So these three properties, and fourth property also we can see. Like if xt is the energy signal, then energy of xt can be found using autocorrelation function, that is given as minus infinite to infinite x of t square dt. So this is autocorrelation at the value of 0. And for power signal, let's suppose if xt is a power signal, then power of xt is given as, this is also Rx of 0, that is equal to limit t tends to infinite, and here is from minus t by 2 to t by 2 mod of xt square dt. Okay, so and also like there is one property, a Fourier transform of Rx tau, that is the x of x omega, like autocorrelation function and power spectral density makes Fourier transform pair. So x omega is power spectral density. So we know that like this we can see Rx tau is equal to x of tau convolution with x of minus tau. So now Fourier transform of Rx tau, that is equal to x of omega into x of minus omega, because convolution in time domain becomes multiplication in frequency domain. And in this case, if let's suppose xt is a real signal, real and even, then x of minus omega is equal to x conjugate of omega, and this will become x of omega into x conjugate of omega if xt is the real and even. If xt is real and even, then what happens? X of minus omega will become x conjugate of omega. So now this will become mod of x omega square, that is the magnitude, and that is the power spectral density x omega. So here the Fourier transform of Rx tau, that becomes x omega. So these are properties of autocorrelation function. This is mainly taught in the communication also. And we will see the formula for cross correlation function also. I think the timing in the recording session, because of my Ubuntu, it is changed to 12 p.m. But the class is at 5 to 6 p.m. only. Because I'm recording in my laptop, there it is showing 12:20 p.m. So cross correlation, like it is a similarity between a signal and shifted version of other signal. So like there are two signals, xt and yt. So we can give the cross correlation as rxy of tau, that is equal to integration over minus infinite to infinite xt y of t minus tau dt. And this can be also written as x of t plus tau yt dt. So this can be written as x tau convolution with y of minus tau. So, this was cross correlation between xt and yt. Now, similarly, if like it is asked to find cross correlation between yt and xt, then it will be denoted as ryx tau. So that will be minus infinite to infinite integration of yt into x of t minus tau dt. That can be also written as we can add t plus tau in y and x of t dt. So this will become yt convolution with x of minus tau. So in this way we can represent ryx of tau. So now we will see like some of the properties here for cross correlation function. So it is also even function, like here rxy of tau, that is equal to ryx of minus tau. And the second property is rxy of tau, that is always less than equal to rx of 0 into ry of 0. That is autocorrelation of x and y at 0. So this is always less than equal to this. And the third is, if ryx is equal to rxy is equal to 0, then xt and yt are said to be orthogonal. Why? Because this signal does not have any relation. That's why we are finding cross correlation between two signals. So if r of xy is equal to 0, then xt and yt are orthogonal signals. So here we can see the proof also, like rxy tau, that is given as x of t y of t minus tau dt. Okay. So here when we substitute tau as 0, so we will get minus infinite to infinite xt yt dt. So now here Rxy is equal to 0. This means this Rxy of 0 is equal to 0. This means this integration will turn to 0. And here you can see if this term is equal to 0, this means xt and yt are orthogonal to each other. So these are the properties of autocorrelation function and cross correlation function. Also, like we will solve one question that will like with that we will see what is phase delay and group delay also. So with that question only we'll understand this concept. So let's suppose a linear phase channel with phase delay Tt and group delay Tg must have following relation. The options are given like option A is Tp is equal to Tg is equal to constant. Option B is Tp is directly proportional to frequency and Tg is directly proportional to F. Option C is Tp is equal to constant and Tg is directly proportional to F. And option D is Tp is directly proportional to F and Tg is equal to constant. So here Tp and Tg is the phase delay and the group delay. So like we know that the phase delay Tp, this is given as minus of angle of h omega naught divided by omega. Okay, and this is the phase delay. Basically, it is the time delay experienced by a signal when the signal passes through a system. Okay, and that can be found using this. And the group delay that is given as Tg of omega. You can write in terms of omega. That is equal to minus of d omega and angle of h omega. So this time delay is when an input signal that contains component with a different frequency passes through a system is referred as group delay that is given as Tg of omega. So here in this question what it is asked, a linear phase channel with phase delay Tp and group delay Tg must have. So if it is a linear phase, so let's suppose phi omega, the linear phase, this means minus omega of T naught. Okay. Now we have to find the phase delay that is Tp that is equal to minus of angle of h of omega naught by omega naught. So here this is our h of omega naught basically. So this will become here what we have assumed as a minus of omega T naught T naught by omega naught. So it will become minus of T naught. So here its minus sign is there, so it will become minus of minus. So it will become plus T naught.
Sir, omega means sir, this the fundamental question.
It is just like a frequency component here. So in this like f is the frequency here. So with that that is omega naught we have to find here.
Okay.
So now for group delay. Tg, that is equal to minus of, we have to first find the derivative of it and then with respect to d omega. So we will do minus of d of omega naught t naught divided by d of omega naught. So it will become minus of, sorry, this is minus already here. It will become plus of t naught. So in this case, Tp is equal to Tg. So option A is correct. So this was the question based on this. So in today's lecture, I think we can conclude here only. In the next lecture, we will study about the next like week ninth of this lecture series. So I will share this video on YouTube and the link will be shared on the NPTEL portal. So thank you everyone for watching. We can close the lecture today.